Hi, everybody. Let me welcome Philipp from LINSTOR. He will be talking about DRBD deep dive now, and I'll just hand it over to him.
Oops. Thank you for the introduction. Let's jump into it, right? So at Linbit, we do 4 things. So protecting data, that is by replication, keeping services online. In the context of CloudStack, that's obvious. CloudStack takes care of the HA part. With behind Shape Your Destiny, I'm hiding that we are an open source company. So everything we do, everything I talk about today is open source. And the deep dive is what we will do now. Yes. Yesterday, René had a presentation, and he was talking about the integration of our storage stack into CloudStack. So it starts from the top. It starts with the driver that is more or less, well, which is part of CloudStack. Then it goes into a layer that's called LINSTOR, and LINSTOR does the orchestration necessary for our data path. And today we will deep dive into the data path. And the data path, that's called DRBD, and that's a driver for the Linux kernel. So on this nice slide, I have 2 machines, this box around it, that is the Linux kernel. And in the case of CloudStack, you won't have the buffer cache and the file system up there. You have there your KVM process sitting there. And KVM, when it submits I/O, that goes directly to DRBD. And then DRBD starts with its magic. And well, what is the purpose of the exercise we're doing? We want to replicate the data to have it highly available, right? And the background where we're coming from is we really love hyper-converged architecture, right? We love to co-locate your KVM process with one location where you store the data. Why is that? Because when you read something, we can carry out the complete read operation locally and do not need to create traffic on your network. So this is the background. This is why I'm concentrating on it. But we are not limited to that. So you can also use this whole stack in a completely disaggregated architecture. So we have your compute nodes running your KVM processes, strictly separated from the storage nodes, hosting your SSDs, and you send everything over the network for read and write. Which has also its advantages, but today we're talking about this stack. And well, and if I/O requests arrive here, I have write requests. That's the interesting one. We send it down, we send it over the network to the peer's disk, and an acknowledgement comes back all the way. So if we look at that, it is like this timing diagram. So it all starts with someone hands us over a write request. It calls into the DRBD driver. Starting from there, we do 2 things in parallel. We submit it to the local I/O subsystem, and we hand it over to TCP/IP. And both of these might do some scheduling or delaying it because maybe the NIC is busy, etc. And when you compare the latency in the end to what it would be if you don't replicate, you get an overhead. And the overhead is sending it over there and waiting for the acknowledgement to come back, right? And all this is happening massively parallel. So you get thousands of these submits maybe in parallel on different CPUs hitting you, and this timing diagram runs in 1,000 iterations at the same time, right? So this is what happens in the I/O stack. And, oh, why is it blue? Okay. I don't know what this program is doing on me. So what can go wrong? You know, this is about high availability, so we always need to consider failures. So let's start with the easy case. We are executing such a write operation. We're sending it to local storage. We send it over the network. And maybe it is received by our secondary node. But before it makes it to stable storage, the node goes away. What happens then is, then on the primary, it is expecting this write acknowledgement, right? It's not coming. So some timeout expires. Then the first action is, OK, is the node really away? So it sends like an in DRBD protocol ping to the other node. For that ping, it has a smaller timeout, so that expires as well. So in default configuration, this takes 6.5 seconds. You can make that smaller, like a single second. And then it would complete the I/O request. But we need to do something, right? We need to remember that we were not able to replicate this write. So this brings us to one of the requirements I'm coming to. We need to remember that. And in DRBD, we have what we call a change tracking bitmap for this purpose. And I will come that on the next slide again. What else can happen to our timing diagram? It can also happen that we are working on a write request. We send it to our local SSD, and we send it over the network. So it makes it over the network. It's traveling on the Ethernet, right? And while it is traveling there, the primary machine crashes. So what's happening? The secondary completely executes the write operation, but to the application, which gets restarted, blah, 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 to the application, this write never executed. It never happened, right? Because it was never completed by the I/O stack. So if we recover in this situation, what we need to do is we need to roll it back, right? So this is like the second requirement, how we can recover from failures. So I hope my timing diagrams and my talking brought the point across. We need to handle two scenarios. We need to be able to roll forward. That is the change tracking bitmap. A node goes down, it comes back. How can we reintegrate it? We need to send over what was written in the meantime, change tracking bitmap. But also the other way. If the primary crashes, we restart the application somewhere else. It restarts at a point where this last write never happened. So it's in order to reintegrate that node, we need to do this rollback. And for that, we have the activity log that does so-called intent tracking. So we save and stable storage what we are going to do. And now this brings me to the two main data structures we have in DRBD for this purpose. So in the metadata, we have a bitmap. The bitmap, in concept, it's very, very easy to understand. So we have 1 bit for 4K of storage for each peer. And that's an in-core data structure. We have that in memory. We also have it on stable storage in the metadata. And here it makes a big difference. If our backing storage is a block device itself, SSD or a rotating disk, or if it's a persistent memory device. Because in case it's a PMEM device, we can directly map it. We don't need to load it, right? And also modifying it is a lot easier, right? Because modifying something on block storage requires a write. Better you do a 4K write these days. Don't do 512-byte writes anymore. Not a good idea. On a PMEM, it's very easy. You write to memory, that's it. Well, not exactly. You write to memory, is something the CPU virtualizes for you because it goes only to a cache, right? The cache will not survive a machine crash. So we need to make sure that we flush the cache. And I think it took even an iteration of Intel CPUs to get all that right. So now we can flush a cache line and wait until we are sure it's really in the DIMM and not in some spoofable cache, CPU cache. Okay, so that's the bitmap. I think in concept, it's very easy to grasp. And you don't need to care about the details, like when we write it. Mainly the only thing you notice is if you have a really huge DRBD volume and you attach it, you will notice it takes a little time. And this little time it takes that's mainly reading the bitmap, because we read it all at once in the moment we attach a huge device. Well, any device, but you only notice it was a huge one. The other data structure is the activity log. It is like a ring buffer. So it's a small area. We append 4K writes, and then we start over at the beginning again. And in the activity log, we see our whole storage volume as a set of 4 megabyte extents. And for each of them, we remember, okay, this one was under I/O, it's active, and this one is not under I/O, it's cold. And in the moment we have a primary crash and we recover that machine, we read this activity log, we find out which extents were hot, and for all the hot extents, we then request them from the surviving nodes to send us over the data. So this is the rollback process, right? And the main tuning knob to optimize this for your specific use case is you can decide how many of those 4 megabyte extents might be active at the same time. So allowing a bigger number gives you better performance because you will see less updates to the activity log, right? A smaller number gives you more updates to the activity log. So you should go for the biggest number, right? But it's a trade-off. So where do you pay for the trade-off? You pay when a crashed primary reintegrates. So if you gave a biggest number, you will get a bigger resync at reintegration time, right? But as a general rule of thumb, our default values for these tuning numbers, they are very old from HDD time. So these days, increase it. It will help. Okay, and apart from that, what else is in the metadata? We have the super block. So there, lots of other information is in. There is the information that allows us to find out if it went into a split brain, the infamous split brain on DRBD, right? Fortunately, these days, this is no longer really an issue if you do it right, because you get quorum enabled, and LINSTOR does that automatically for you, so you don't run into split brain situations anymore. Okay, so my title here was I wanted to do a deep dive. So next question is, where do we put this metadata? And by default, because it's the easiest option, is what we call the internal metadata. So that means LINSTOR gives us a logic volume from our volume group, and it adds a little bit at the end, and DRBD will put the metadata there. So what's the advantage? It's very easy. It works out of the box. You don't need to care about anything. And by the way, we put the metadata at the end. That has a nice advantage. If you try to mount this, let's say there's a file system on the volume, right? And if you completely remove DRBD from the picture, you still can mount this logic volume because the file system itself, everything is nice. It finds its own superblock. It just recognizes, oh, I'm not using the whole device, but that's not a problem. So all file systems do that easily. Same goes for virtual machine image, right? So this is one of the properties of DRBD. It is completely transparent to what you have on disk. And if everything goes wrong, you can recover your data, right? So that's the advantage, easy to use. The other advantage is if it happens that you lose a storage device and you replace it, right? Also, the metadata is gone with the data. So all the other components of the stack automatically do the right thing. Now, let's look at the other option. We call that external metadata. So here, you have one logic volume having the actual data and a second logic volume used for the metadata. The big advantage is we can put the metadata on a different on different storage media, right? Disadvantages, of course, if you lose these storage devices, you better tell the system that now you replaced it. So if the metadata stays in place, DRBD would assume, oh, my copy is intact, right? So there is a little pitfall. Now, I think 2 slides ago I mentioned PMEM. So just that you, one option to put DRBD metadata is NVDIMS, persistent memory. So just in case you're aware of that, so as a memory DIM, right, you put that into a DIM slot. It is physically, it contains DRAM plus an NAND and a power source that allows it, in the moment when the machine fails, it uses the power from the supercap to flush the content of the DRAM into the flash, right? When you power on the server again, it restores the content of the DRAM from the flash. But as long as the server runs, it is as fast as DRAM. There is no difference in speed, right? So there are different vendors offering this. And this makes a lot of sense if you have your servers with, I don't know, 16 slots for DIMMs or even more. It makes sense to add one of these NVDIMMs just to put the DRBD metadata there. Yeah, and yeah, here, so as a practical takeaway from this part, I collected the different tuning options, what you can do to optimize how DRBD uses the backend device. So one is to disabling flushes, right? So maybe I should explain what flushes are in the storage stack. So in the storage stack, when you write something, I start the explanation with a hard disk, but the same is also true for the latest and greatest NVMe drive. So when you write something, the first is the request is passed down to the hardware. A DMA is initiated from your DRAM to the memory on the storage device, right? And when this operation is finished, control goes back to the operating system and it might initiate the next DMA from the machine main memory to the memory on the storage device. And then behind the scenes, the hard disk writes this from its own memory onto the rotating media. So that's a 2-step process. But from the operating system, you get the completion in the moment it's transferred to the memory on the hard disk. Because you're now free to reuse your main memory for something else, right? The data is transferred. But it's not yet crash safe, right? It has not yet made it to the disk. And therefore, we have these flush commands. And the flush command means you do your writes, and then you send the flush, and the flush takes a little while, and it guarantees you, OK, now it's on stable storage. But there are storage stacks around where the flush command isn't necessary. For example, when you have a RAID controller, and the RAID controller has a battery backed up write cache, right? Then you don't need flushes. And what's a little bit unfortunate, these RAID controllers still execute the flush, but actually you don't need it. So therefore, we have all these tuning knobs where you can disable flushes. But you really need to understand when it is valid to disabling flushes, right? You shouldn't do it just, oh, it makes it faster, perfect. OK. The other things, peer slots, new resources. That's a ugly named property, but on the earlier slide, I had it that is bitmap, that we have the bitmap per peer slot. And all this bitmap that is allocated up front. So in the moment we create the resource, and LINSTOR has a default of 7, which is quite high, quite heavy. So for big resources, you want to reduce that. Then the activity log extends. I think I talked about the number of activity logs. As I already talked about that. Yeah, and last but not least, that enables you to put the metadata on a different storage device. So storage media, yeah. OK, I was talking so much about storage devices. Now let me use my last 6 minutes for the networking side of things. I had this illustration already, but in the previous one, you saw here TCP/IP and here NIC. So there is another networking world around, and they gave the things different names. Now it's called RDMA and HCA. Host, oh, I forgot it. Host something. Host adapter. So from this point of view, it's about the same thing. When you buy the RDMA adapters, they're a little bit more. They will cost a little bit more than regular Ethernet adapters. Probably the highest challenge is the differences in networking. So either you go all InfiniBand, you have different cabling, different switches. These days, RDMA is also possible on Ethernet, but the Ethernet switches need additional features. So it feels a lot more at home, but it's still not exactly the same thing. And but this RDMA stack, it comes with a few advantages for us as software developers. So it gives us a lot better control how the transfer over the data over the network works. So the API is a lot richer, gives us more power, but with power comes complexity, right? So our code for RDMA is about double of what we need for TCP/IP. So it's more complex. Both stacks can do zero copy send, zero copy receive. In the TCP world, difficult topic. We have implemented it only for the control channel, but that's boring. The data channel would be interesting, not possible in the TCP world. In the RDMA world, yes. So there is no copying of the data on the receiving side. And RDMA write. That's interesting. So RDMA writes, we can use that in our storage world for executing remote reads. So how comes that? So on a machine, and let's say it's a disaggregated architecture. So you have the DRBD device, but we don't have a local copy of the data, right? We get a read request. And with the read request, we already get a buffer. The kernel wants to have the data in this buffer and not in somewhere else in memory, right? So what then DRBD does, it sends a request to one of the nodes that has the data, and with the request also goes the memory address where the data should go. And then the other side does a RDMA remote write and fills the data in. So a block read request maps to an RDMA write request of the server. Makes a lot of sense, right? So this is completely impossible in the TCP world because here the stack manages the buffers for you. It's possible in the RDMA world. We will add that as well. And then on the feature side, yeah. On the TCP side, we can use KTLS, so TLS encryption in the kernel. On the RDMA side, maybe there is something possible, currently out of scope. Yeah, so here the takeaway is if you want to optimize what it takes on a network, think about RDMA. What else can we do on the network side? Multiple paths. So both implementations, TCP and RDMA, support multiple passes for a single DRBD connection. So usually you would put that on different NICs and maybe also on different networks, different switches, different failure domains for the network, right? Aggregates bandwidth, increases availability, right? That's easy. We also have customers using multiple paths over a single NIC when they run DRBD in the public cloud. That the cloud provider happens to have traffic shaping for individual TCP streams. Then multiple TCP streams help, right? And also on the RDMA world, it makes sense to have multiple passes over a single HBA to fully utilize the hardware. Okay, so what's my time budget? It's over. Okay, so this is obvious. Users for databases. By now you know why it's so fast. And here are the numbers. You can follow the link when Jamie sends you the slides afterwards. Thank you.
Thank you, Philipp. Thank you, Philipp. Now we do have just a couple of minutes for questions. So, any questions from the room?
Vido.
So regarding the persistent memory, where can you source them? Because I know Micron and Intel, they create this persistent memory, but it's pretty difficult to source these components.
Yes, it's difficult to source them, I agree. Micron and Intel produced 3D cross-point PMEM, and I'm not referring to that. and that was discontinued, right? But I'm referring to these that combine DRAM with flash. And they are still produced by... Sorry?
Not the Optane.
Yeah, not Optane, right. Not 3D crosspoint. They are still produced. It's not so easy to get them, but you can get them. And the hardware appliance makers, they get them as well.
Okay, thanks.
Any other questions? Venko, of course.
Thanks. On your, I think, second slide, you showed the workflow for the write operation. Did I understand correctly? Can you complete a write operation and acknowledge the write operation if the network is down? Or if there is an interruption of the network during the operation?
Yes. then
So the DRBD stack will acknowledge to the application that the operation is completed only when it's completed with the local storage, on the local storage, but not replicated to the remote site. Yeah, this one.
You're referring to this slide,
Yeah.
right? Yes, I mean, it depends a lot on your configuration, right? You can configure DRBD to have a write minimum replica count of 2, then it will instead freeze, right? But I'm assuming the configuration that for most people in this room makes sense. You will have a replica count of 2, and you still want to complete this write operation, just
with the local.
With just after it's written to local and after DRBD figured out, okay, the other machine crashed, then it starts this change tracking, and then it completes the write request, yes.
Okay, thanks.
All right, thank you. Unfortunately, we're out of time. One big round of applause once more for Philipp.